Happy day, everyone. This is Orekoya Olusegun, Physics Mathematics Fundamental on YouTube. Today, we are going to, attempt a topic in physics mechanics, and the topic is on the derivation of the uniformly accelerated motion equation by calculus method. We want to derive the uniformly accelerated motion of objects along a straight line by calculus method. Now, we must have this background. The background we must have before we can derive this equation is the differentiation, how to differentiate and how to integrate, basic differentiation, that's the background. Differentiation, that's the basic, and then integration. We must have the understanding of differentiation and integration, the basic one. This particular aspect, I dealt with it in my last video. You can check on that particular video on the basic differentiation and integration on Orekoya Olusegun Physics Mathematics Fundamental as a reference. Now, another thing we need to also have at the back of our mind is that in physics, we define acceleration as an instantaneous change in the velocity with respect to instantaneous change in the time. That's acceleration. We also define velocity as instantaneous change in distance covered divided by instantaneous change in time. This distance covered in a given direction. We should have this at the back of our mind. Now, let's start derivation of the equation of uniformly accelerated motion on a straight line. Let's start with differentiation, acceleration. We know that acceleration is dv dt. By making dv subject of formula, we have dv is equal to a dt. Now, integrating both sides of this expression, we have integral of dv from the initial position u, velocity, to the final position v, or the velocity of that particle along the straight line. Then we integrate a dt from the initial position when t is equal to 0 to any other time t. Now, here, integration of the v is actually v with this limit of the starting point where the velocity is u to the final point where the velocity is v is equal to integration of a dt. In this case, the acceleration is uniform, it is constant, so we can take it outside the integration sign as integral 0 to t dt. So integration of dt will give us a t with the limits 0 to t outside. Now, what do we do with this limit? It's just a simple subtraction. So what we have here, we substitute v into this v, then u to this one, we subtract what we have. When we put v here, we have v, then when we put u here, we say take away u is equal to this. So we have v minus u is equal to a times, when you substitute this one, just be 80. Now, having done that, let's say this one is equation 1. And this particular expression also implies that acceleration a is v minus u divided by t. That is change in velocity in a given direction divided by change in time. We should have this at the back of our mind concerning this expression. Now, let us make v, this final velocity, subject to the formula in the first equation we have here. So in this case, we have v is equal to at plus u. Now, having done that, this particular expression should be also noted. Now, having done that, we can take note of the fact that velocity is a change in displacement divided by change in time, which is the same thing as at plus u. Now, making the s subject of the formula, we have the s, then we cross multiply the t to the other side of the equation, is equal to at plus u dt. Integrating both sides of this equation in the limit, we have integral ds from when the distance or the displacement is 0 to any other point where displacement is s, is equal to integral at plus u dt. So dt simply means our integration is with respect to time. So we have when time is 0 to when time is t. When we integrate the s, we have s with our limit putting outside there, 0 to s. Now, integrating this particular aspect, I've taught us how to integrate in my last YouTube video. We integrate this time by time. When we integrate at, it's going to be at raised to power 1 plus 1 divided by 1 plus 1. Then plus u. We know that this u can be written as ut raised to power 0 plus 1 divided by 0 plus 1 in the limits of 0 to t. 0 to t. So when we substitute this limit here, we subtract. So it's going to be s minus 0 will give us s. Now here we have at 1 plus 1 is 2, at squared divided by 1 plus 1, that's 2. Then plus, when we have this one, t raised to power 1, so this one is simply just ut. This is another equation that we can use when we are dealing with exercise on uniformly accelerated motion along a straight line. Now, having done this now, we want to eliminate a and t with respect to using this expression that we have here, with respect to using when acceleration is b minus c over t. And then we also eliminate t by making t here subject to formula. So the first thing I want to do is that I want to eliminate a in this particular expression I have here. So in the nutshell, my s, which is at squared divided by 2 plus ut, since a that I derived before is v minus u divided by t, I can substitute it here. So in the nutshell, the s now become v minus u divided by t, that is for the acceleration now, times t squared divided by 2, then plus ut. Now, if we open this bracket here, this one become vt squared minus ut squared divided by 2t, then plus ut divided by 1. We know that this t can cancel each of the t here. So t here, we cancel one t here, we cancel one t here. So in a nutshell, we are going to have, when we cancel here, we have vt. Take away, when we cancel one ut here, we have a ut, then divided by 2, then plus ut over 1. Then the LCM here is 2. So 2 into 1, 1 times everything will be the same thing. So our s now become vt minus ut plus 1 in 2, that's 2ut. 2ut. Now, if you look at this ut and 2ut, they are like terms. So 2ut, take away ut, will give us ut. So what we have now is our s will now become vt plus ut divided by 2. By factorizing t out, we have the s becoming v plus u times t divided by 2. This is another equation. Let me call it equation 4. Now, having eliminated a, we want to derive another equation by eliminating this t. Using a is equal to v minus u divided by t. So from a is equal to v minus u divided by t, we want to make this all the formula it implies that our t will now become v minus u divided by a. So we want to substitute this expression where t is given as that. We can put the expression here, or we can equally put the expression in this particular one. Putting the expression t is equal to this here is more straightforward than putting it here. But if you put it here too, we are still going to get the same results. So let's use this one now. So we are now have s is equal to v plus u times, instead of t, we put v minus u over a. That's v minus u divided by a. Then over these two here that we have here. 2 times a, that is 2a. So the s now become 2a. From difference of 2 square, we can see that these terms are the same, except we have plus and minus. We remember this difference of 2 square. Note this difference of 2 square, that anytime we have a square minus b square, it actually means a minus b times a plus b. This expression I'm having here is similar to what I have here. So this expression can also be written as v square minus u square. This is another equation for the distance cover for a body that is moving along a straight line with a uniform acceleration. I believe that we've learned one or two things concerning the derivation of the equations of uniformly accelerated motion using the calculus method. Please kindly ensure that you comment, you share, and you like my video on YouTube. I want you to send the links to your friends, to your relations, and to other people that are in a physics line to learn one or two things concerning this derivation. I'm so glad having you. Orekoya Fumi Olusegun, Physics Mathematics Fundamentals on YouTube. Have a nice day. Thank you.